Hi, everybody. We're going to do the second half of the basic introduction to capacitors. I'm Michel Maharbiz.
And I'm Vivek Subramanian. Let's get started. Where we left off in the last section, we had been talking about capacitors and had just introduced the idea of how capacitors would respond to time-varying signals. Today we're going to pick up on that and look at the implications of how capacitors behave when we apply time-varying signals. So let's get started by considering a given capacitor. Let's say we take a capacitor with some known value, say on the order of 0.6 microfarads or something like that. And let's say we apply a time-varying voltage signal that has this shape. So the waveform we use is this one. Michel, maybe it's a good time for you to review. What are these individual segments?
So it looks like it starts off at 0 and then it begins to ramp up.
Right, so there's a ramp, correct?
And then it's going to flatten out.
So which means, how do we get there?
Guess we subtracted out a ramp.
Correct.
Okay, the opposite direction, of course. And then it's going to begin ramping down. In other words, we subtract out another ramp.
Yep.
And then it flattens out again, which means we added back a ramp.
Exactly.
And very similar to an example we did a few modules ago.
That's right. Okay, so now we've got a voltage waveform that we've built, and it's a time-varying waveform. In other words, the voltage changes as a function of time. Now, let's see if we can use the capacitor charge voltage current relationship to figure out how the capacitor behaves in response to the stimulus. Specifically, you'll remember that we said that the current through a capacitor changes with the derivative of the voltage. So in other words, the current through a capacitor is the capacitance times dV dt. So all we then have to do to find the current through the capacitor is take the derivative of this waveform. So in this region, the derivative is 0. So we see that when there is not any time-varying signal, the capacitor does not pass current, so the current through the capacitor is 0. Then, when there is a change in the voltage, in other words, dV dt becomes some fixed value, there's a jump because of the discontinuity right over here, and then it follows the slope. So since we are in a region of constant slope, we'll have a constant current till we hit another discontinuity where it drops back down now to the non-varying portion, so it's flat at 0. Then, when we have the slope downwards, the current will go negative, and then again, when it flattens back out, it goes to 0. So let's put that all together. What do we have? When the voltage is increasing with time, we have a positive current. When the voltage is reducing with time, we have a negative current. And when the voltage is not varying with time, we have 0 current.
So I guess intuitively, in the areas where there's a positive currents going into the capacitor, you're increasing the voltage on it. Could you think of that as charging the capacitor?
Yeah, in the sense that this current flowing, actually this is current flowing through the capacitor.
Fair enough.
Because the voltage is actually changing, but yes, effectively you are altering the charge in the plates.
Perfect.
Okay, now we've got capacitance, we've got voltage, we've got current. You know that if we have voltage and current, we can figure out power. So now we can answer your question regarding charging the capacitor, because you know that the power delivered is the multiple of the voltage and the current. So we can essentially take these two plots and multiply them into each other, and we get a power plot. And you see that in the case where the voltage and current are non-varying, we have 0 power. Then when we are ramping up the voltage, we are transferring power into the capacitor. So indeed, we are charging it up. Now the interesting thing that happens is look between time points 2 and 4. Here we have a non-zero voltage, but because of the nature of the capacitor, there's no current flow. So we have no power.
That makes sense.
Yeah, so this is kind of an interesting example where the capacitor demonstrates how it allows current to flow when there's time variance in the voltage, but otherwise does not. And the consequence of that is when there's no time variance, there's no power. And then correspondingly in this section, we are pulling power out of the capacitor. In other words, we're discharging it.
Fair enough.
So you see how this works. Now, of course, if the other relationship we have is to calculate actually the relationship related to the energy, which we'll call the work, or W. And that you can calculate from the voltage and current to be half CV square. And the units, of course, will be units of energy or joules. And so if we take the voltage curve and we take the square of it and we multiply it by capacitance, what you find is as you charge the capacitor up, you are increasing the energy on the capacitor, then it stays flat, and then you pull it out.
Which also makes sense by just looking at the power, right? Because we know that energy is essentially the total amount of power that's been transferred over some span of time, right? So power in this case is being transferred into the capacitor, and so as that happens, you're getting energy building, and then as soon as there's no more power going in or out, in other words, this is zero, the energy stops and it's at a fixed amount of energy in that capacitor. And when we start to transfer power out of it, you can see that this thing drops back down.
That's right. And you can also think about this in the following way. Remember, as Michelle pointed out, when we have the voltage ramp up, we are charging the capacitor. So what we are doing is we are storing energy in the form of an electrostatic field that develops between the plates.
Cool. All right, let's look at this in a bit more detail, I guess, with expressions would be ideal. So let's start with this expression that Vivek was just talking about that we've seen before. I, the current, equals C, the capacitance, times dV dt. And let's rearrange it to this form. We can integrate this. We can integrate both sides of this with respect to time from some initial arbitrary time point t0 to t. So we do that on both sides, pretty straightforward. And when we take that integral, effectively we can integrate for the voltage. So this is what you would expect from this expression. If you start with dV dt and I, it follows that the actual voltage equals the voltage at some initial time point plus this integral of current, you see right here, and of course C doesn't integrate, so you put it out. So it's 1 over C, the integral from t0 to t of the current.
Okay, so now I guess that initial voltage is the voltage that was on the capacitor at time t0 when I started the integral.
That's right.
Okay.
That's exactly right. So whatever it had initially, that plus the voltage at some final time is going to be that plus whatever change in voltage occurs from the current, either going in or out, or rather negative or positive through it. That's the correct way to say it. Now the integral of current, of course, over time is nothing but the net charge flow into the capacitor, and we can call this Q, right? This part right here. As you know from your earlier modules, this is just the net charge flow. And so you can break this down and see that the voltage now at some time t is equal to the initial voltage at wherever you started your integration or wherever you started your point of interest, plus the net charge flow divided by the capacitance. So the total amount of charge, whether charge was brought in or charge was brought out, which is something Vivek was highlighting in the last slide.
Okay, that sort of makes sense to me because that integral means if we have portions of the I that are positive and portions of the I that are negative, because we're integrating over the entire span of them, we'll get a net result. In other words, we'll be adding or subtracting charge depending on what we're doing.
That's right, and that's reflected by this Q. It's a net charge flow. So if I put in 5 and take out 3, 2 is the net.
Okay, so now, having understood the basic time variance relationship, let's constrain our analysis to a very specific and extremely important case, which is how it responds to an AC signal. Now, Michelle, maybe it's worth repeating what an AC signal is.
Well, an AC signal is just a sinusoidal signal. So it's going to have an amplitude, it's going to have a sinusoidal function like cosine or sine, and it'll have a frequency omega naught. And of course, there can be an arbitrary phase shift, but for this example, we're not going to put one in.
Right. So the key point is this is not just a time varying signal, but it's a time varying signal with a very specific shape and periodicity. Now, we have therefore an equation that describes the voltage, which is V of t is equal to V0 cosine omega naught t, where, as Michelle pointed out, there's an amplitude V0, it's sinusoidal in nature, and it has a frequency omega naught. We can take this and plug it into our current equation, and we know that the current through a capacitor is just C dV dt. You know that the derivative of a cosine is just the sine, and since the multiple is omega, we'll bring the omega naught outside. And so what we get is the current I through the capacitor when subjected to this sinusoidal input of a voltage will be minus C V0 omega naught sine omega naught t. Now, what's kind of interesting about this is you notice something pretty interesting. We started with a cosine, now we have a sine. So you know from your basic trig that there's a 90 degrees phase shift with those. So in fact, what we find is that the current in a capacitor is out of phase with the voltage, and in this system where we are looking at the specific relationship between the voltage in a capacitor and the current at that capacitor, it's exactly 90 degrees out of phase. And it's 90 degrees out of phase because of the 90 degree phase difference between a cosine and a sine. Now that turns out to be important. One way you can see the importance is, of course, to look at the power. If we look at the power flow onto the capacitor, which is the instantaneous power, P of t, is going to be V of t times I of t. It's the multiple of these two equations. So you'll notice that it has a cosine omega naught term and a sine omega naught term. Now you know, of course, how to convert that from your trigonometry into a sine term on its own, and that is, in other words, we can rewrite this as minus CV naught squared over 2 times omega naught sine 2 omega naught t. Now, Michelle, do you notice anything unusual about the periodicity of that signal?
Well, so what I noticed is that from voltage to current or current to voltage, you maintain the same frequency, so this omega naught. So you get cosine or sine, and those are just a phase shift, same exact frequency. But the power is oscillating at twice the frequency.
Correct. So you hear the coefficient inside the cosine was omega naught. Here the coefficient inside was omega naught, but here it's 2 omega naught. So you're correct. What happens is the power switches at twice the frequency, and the reason for that is because of this 90-degree phase difference, which means the zero crossings are shifted with respect to each other. Now we can put that all together, and then we can integrate to find the energy flow into the capacitor. You know that the energy is just the integral of the power with respect to time. So if we perform the integral of this AC signal with respect to time, and we solve it, voila, we find that it pops out a net energy of 0. Think about what this means. What's happening is any energy that we're storing on the capacitor during one part of the cycle, at some part of the cycle, in other words, the corresponding opposite part, we will withdraw from the capacitor. So what ends up happening is, because of all these positive and negative going cycles, we end up with a net energy on the capacitor of 0.
So we're sloshing energy in and out of this thing at the same, in a sinusoidal fashion, so that makes sense. Okay, let's do a few simple slides to wrap up this module that give you some relationships with capacitors in series and in parallel. So let's say we've got this situation here where we've got a voltage source and 3 of these capacitors that are mounted in series. And what we'd like to do is ask whether there's an equivalent circuit that captures all these 3. And of course, it turns out there is. These 3 can be modeled as a single capacitor, C equivalent. And to see how that works, it's pretty straightforward. Recognize that the current IS is the same through all capacitors. There's no additional extraordinary nodes or other branches.
And that's because of current continuity.
Exactly, yeah. There's nowhere that this current can go. It's just going to go straight through these things. And so as a result, I can say that IS equals, and then for each capacitor, C dV dt. So IS equals C1 times the derivative of the voltage across that capacitor, d1 dt, and that also equals C2 times the derivative of V2 with respect to dt, with respect to t, and it equals C3 dV3 dt.
And so that's because we have the 3 capacitors. The same current must be flowing through all 3 capacitors. Therefore, they must be equal.
That's right. And we also know by KVL that Vs, the voltage between nodes 1 and 2, must equal the voltage drop across all 3 of them, V1, V2, and V3, and that's written for you right there. And so once we make once we understand that, if we begin by the assumption that, and that's the way I like to think about it, if I start by assuming that this can all be modeled by one capacitor called CEQ, it must be true that the current IS going through that one equivalent capacitor follows the same relationship for our capacitor. So IS must equal CEQ dV ds dt.
And right? Now Vs is the voltage across the entire string.
Exactly, and that's the trick. The trick is that the voltage across this equivalent capacitor is this Vs here, and I know that I can write that using this by the KVL I did above. So dV1 dt plus dV2 dt plus dV3 dt, right? And now once I've got it in this form, I also know that each of these 3 terms, I can look up here, and dV1 dt equals IS over C1, and same with dV2 dt, it equals IS over C2, and dV3 dt equals IS over C3.
Okay, so if I understand correctly, what you're doing here is you're substituting by looking at this top equation up there, you find what dV1 dt is, and then you just plug it into the bottom equation.
That's right.
Okay.
So we use KVL, we use the initial KVL to map the dVs to the 3 voltages across here, and then we recognized the relationships between the current through each capacitor and its voltage, and got this here. Now once I got it in this form, it's actually pretty straightforward to solve for C equivalent, because I've got IS on the left equals C equivalent in parentheses and IS is up here. These can be factored out, and as you can see by inspection, in the end, they'll drop off, and I'll just find that 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. And so the fundamental piece of this is capacitors in series kind of behave like resistors in parallel.
Makes sense, because I recognize that. I remember when we were talking about resistors, we had the resistors in parallel as the reciprocal of the sum of the reciprocals.
That's right. So you get used to looking at capacitors in series and think of them dealing with them like resistors in parallel.
Makes sense.
Okay, capacitors in parallel. You want to try this one?
Sure, this one should be pretty straightforward. I'm going to take a guess that a capacitor in parallel is going to take the same form as resistors in series.
Okay.
And that turns out to be true. So we can use a similar methodology. In other words, we'll formulate a circuit where we have now a source applied to 3 capacitors in parallel, and now we'll recognize that in this case, rather than using a KVL, we use a KCL, and we recognize that all 3 capacitors will see the same voltage across them. Similarly, because of current splitting, we can write that the total current going into this combination of capacitors is going to be the sum of the individual currents, I1, I2, and I3, because those are 3 separate branches between the same pair of nodes. We can then write IS, the total current, is equal to C1 dVs dt, the current through capacitor C1, plus the current through capacitor C2, plus the current through capacitor C3. So we see that we have 3 differential terms in our equation. Now, let's put that together. We know, of course, that if we were to replace this with a single equivalent capacitor, we would write it as IS is equal to C equivalent dVs dt. So you can guess what we're going to do now. We're going to set these two equal. We set them equal, and we've got C equivalent dVs dt is equal to this equation over here, and the dVs's drop out, and what you're left with is C equivalent is equal to C1 plus C2 plus C3. And if you had even more capacitors in parallel, it would just keep going all the way to Cn. So now you see then how this capacitor in parallel strategy works. Look at this equation. It looks similar in form to resistors in series. In other words, capacitors in parallel just sum together to form one equivalent capacitor.
So what you're saying is if I've got a 3 microfarad capacitor in parallel with a 4 microfarad capacitor, it looks like a 7 microfarad capacitor.
Exactly right.
Okay, fair enough. Last thing, and we're going to leave this mostly as an exercise for you to do. But recalling that what a voltage divider looks like, if you recall, if I have a source, a voltage across 2 resistors, this is voltage Vs represented by the source, I can of course write what the voltage, corresponding voltage drop across, say, this resistor is, V2, as R2 divided by the sum of the two of them, R1 plus R2, times the original, the independent source, okay? The voltage drop across both of them. And likewise for this, R1 divided by R1 plus R2. It turns out if I were to do this for an AC source for 2 capacitors in series, I'd get kind of the opposite effect. In other words, the voltage across this second capacitor, let's say I have 2 volts across both of them. This Vs is 2 volts. So there's 2 volts between this node here and this node here. The question we're asking is how do those 2 volts split across the capacitors? And so let's take V2. So the voltage across this capacitor is in fact those 2 volts, Vs, times C1 in the numerator. See the difference?
Yep, I see.
Divided by the sum.
I see what you're saying. So here, the voltage across the second capacitor is calculated from the capacitance of the first capacitor.
Yeah, I think about it this way. In the voltage divider case, the bigger I make this one of the 2 components, the bigger I make R2, the more voltage is going to drop across there. But the bigger I make this, the more voltage drops across the other one.
Right, because capacitors in series show reciprocal relationships.
That's exactly right. But we'll leave it to you to figure this out. It's a good, fun, quick exercise, and this is one of those easy things that's nice to remember as an electrical engineer. So we're going to drop off here with capacitors, and we'll see you pretty soon with inductors.
Thanks a lot. Take care.